So good morning, my name is Nick Legler and I work as a fish biologist with the Wisconsin Department of Natural Resources out of Sturgeon Bay. And today I would like to just provide some updates for the Lake Michigan Salmonid Working Group. So the primary role of the Lake Michigan Salmonid Working Group is to annually compile and analyze lake-wide data that can be used to help guide fisheries management decisions, specifically for Chinook salmon stocking levels. And the approach that we use for this annual evaluation is called the Lake Michigan Chinook salmon to alewife predator-prey ratio analysis. And we just recently, within the past week, completed updating the predator-prey ratio with data through 2017. So today I'll just provide a basic overview of the methods of the PPR, and then I'll also share these recent results. So updating the predator-prey ratio analysis each year involves a pretty significant effort by staff and agencies from all around Lake Michigan, so I'd just like to acknowledge and thank all the people that helped out. These efforts involve providing the data as well as collaborative efforts to do the analysis. And these contributions were made by members of the Lake Michigan Salmonid Working Group listed here, as well as many additional staff from around the lake. And I'd especially like to thank and acknowledge sort of the unofficial modeling team within the Salmonid Working Group. So Dave Warner, Chuck Madenjan, Jory Jonas, Ben Tershak, Eob Sahaya, and Rick Clark. So the predator-prey ratio analysis was just recently developed in 2012 to 2014, so it's a relatively new approach. We've all had to kind of learn as we go in terms of updating the analysis. I think we all learn a little bit every year, we get a little bit more efficient at it every year, but regardless it's a pretty big effort and it's typically kind of pushed down to the wire. We just completed the modeling results late last week, and so a lot of these results are kind of hot off the press. So thank you to the modeling team for pushing through to get it done. So the predator-prey ratio analysis is a ratio of total lake-wide biomass of Chinook salmon divided by total lake-wide biomass of alewife, and it allows managers to evaluate the balance between Chinook salmon, a dominant pelagic predator in Lake Michigan's ecosystem, and alewife, which is the Chinook salmon's predominant food source. So generally, a low ratio suggests an ecosystem with few predators relative to a high abundance of prey or alewife. A high ratio suggests an ecosystem with many predators relative to scarce prey. And an intermediate ratio is somewhat of a management goal or a target that represents a balanced predator-prey population. And before I share the results of the actual predator-prey ratio, I'd like to take some time to look at the separate components of the predator-prey ratio individually, starting off with Chinook salmon biomass. So in order to calculate total lake-wide biomass of Chinook salmon, we use a statistical catch-at-age model, and the catch-at-age model actually produces estimates of abundance by age, which then get converted to biomass and used in the ratio calculation. And this slide just highlights the several lake-wide data sets that feed into the catch-at-age model for Chinook salmon. And before I show the actual modeling results, I'd like to just highlight some of these data sets, starting with numbers of Chinook salmon stocked. So this slide shows the total numbers of Chinook salmon stocked into Lake Michigan from 1967 to 2017. This stocking peaked at about 7.8 million Chinook salmon in 1989, and since has been decreasing following several stocking reductions that have been designed to try to balance predator-prey in the lake. So in 2017, 1.37 million Chinook salmon were stocked in Lake Michigan, and this was actually the fourth lowest stocking level for Chinook salmon in this time series. So in addition to stocked Chinook salmon, we know through various marking and tagging studies that there are a fair number of wild produced Chinook salmon in Lake Michigan. Recent estimates from Matt Cornish with the U.S. Fish and Wildlife Service and the Great Lakes Mass Marking Program have suggested that at age 1, about 50% of the Chinook salmon in Lake Michigan are actually wild produced fish. This number has typically been right around 50%, but has varied a little bit. In 2013, it was about 64%. In 2014, it was about 38.6%. So most of these wild salmonids, these wild Chinooks, are likely coming from the tributaries in the state of Michigan and also Canadian waters of Lake Huron. And this figure just shows the wild fingerling estimates in white compared to the stock fingerlings in blue. So annually, during recent years, there's been about 600 to 700,000 Chinook salmon stocked into northern waters of Lake Huron. And also with the Great Lakes Mass Marking Program, we have estimates that about 95% of those fish stocked in northern Lake Huron are actually moving over into Lake Michigan. So forage biomass right now is low in both lakes, but it's thought that conditions might be a little bit better in Lake Michigan, so likely those Chinooks are coming over into Lake Michigan to feed. And collectively, all of these different sources of Chinook salmon contribute to Lake Michigan's fishery, and all of these different sources of Chinook salmon feed into the catch-at-age model for Chinook salmon. So next, I'd just like to do a basic comparison of numbers of Chinook salmon stocked to targeted salmoning boat effort in terms of hours fished, and harvest in terms of numbers of Chinook salmon harvested. These are all lake-wide data sets. These are all data sets that feed into the catch-at-age model. And again, stocking has generally decreased since the 1980s. Effort in terms of hours fished decreased during the 80s and 90s, but subsequently has remained fairly constant. We did see a slight step down in effort in 2008. In 2017, our total lake-wide effort was 2.18 million angler hours, and this actually was the lowest effort on this entire time series. And harvest has fluctuated up and down quite a bit through time. During the 80s and 90s, we actually saw decreasing stocking, effort, and harvest. During this time period, mortality rates for Chinook salmon were generally high due to nutritional stress and associated implications with bacterial kidney disease. Subsequently, despite decreased stocking and relatively constant effort, we actually saw an increase in harvest as conditions in the lake improved. And during recent years, we saw some record high harvests for Chinook salmon in Lake Michigan. In 2005, over 800,000 Chinook salmon were harvested, and this was actually the highest harvest on this time series. 2012, we also had a relatively high harvest with about 708,000 Chinook salmon harvested. So this is an angler contributed photo from 2012. This scene was fairly common in 2012. A lot of Chinook salmon were caught. A lot of bag limits were filled. Fishing was generally pretty good. This was actually my first year on the job working for the department, and I distinctly remember that anglers were pretty pleased to be catching a lot of Chinook salmon. This is also an angler caught Chinook salmon from 2012. And although this is a very extreme example, a lot of the fish that we saw in 2012, both from angler surveys as well as our weir assessments, saw small Chinook salmon in 2012. Certainly there are a lot of factors that impact fishing success, harvest, catch rates in Lake Michigan, but I think a pretty simple explanation for why fishing was so good in 2012 was that Chinook salmon abundance was high, forage biomass was low, and the fish were generally hungry and pretty easy to catch. 2012 was not that long ago, and a lot of anglers pretty distinctly remember this. I think for some anglers it set the bar pretty high, but it was probably unsustainably high. And since, we've seen a decrease in harvest. In 2017, 149,000 Chinook salmon were harvested from Lake Michigan, and this was actually the third lowest harvest on the time series. So all of these different data sets that I just shared, plus some additional ones, feed into the statistical catch-at-age model for Chinook salmon, and they produce an estimate of total lake-wide abundance by age. So this figure shows those abundance estimates. So we have abundance by year. The white line is age 1 Chinook salmon. The blue line is ages 2 to 5. and this is updated through 2017. And I'll just highlight that the yellow dots on this figure and all the figures throughout this presentation will indicate years that a stocking reduction decision was made. So for example, in 2012, a decision was made to reduce Chinook salmon stocking by 50%. Subsequently, that stocking reduction was implemented in 2013. So you'll see the yellow dot here on the year the decision was made, which is 2012. So these abundance estimates by age get converted into biomass by age and are summed to produce a total lake-wide biomass of Chinook salmon, plotted here through 2017. Generally, we saw very high biomass of Chinook salmon in the 2000s. This biomass actually peaked in 2013 at 14.4 kilotons, but subsequently, following stocking reductions, this biomass has come down. In 2017, our estimate was 4.7 kilotons of Chinook salmon lake-wide, and this was the lowest biomass estimate that we've seen since the 1970s. So next, I would like to focus in on the alewife component of the predator-prey ratio. So similar to Chinook salmon, we have a statistical catch-at-age model for alewife. While a traditional catch-at-age model looks at catch-at-age, the catch component of the alewife catch-at-age model is actually consumption. So we have a statistical catch-age model for each one of the major salmonids in Lake Michigan, and these produce species-specific estimates of abundance. And based on those abundance estimates, based on the size of those predators, based on the diet proportions of those predators, we can essentially calculate how many or how much forage must have been present and consumed in order to have achieved the observed growth and size and abundance. So this figure here just shows the consumption estimates by all of these different predator species, and I'd like to acknowledge that throughout much of this time series, Chinook salmon have by far been the dominant consumer of prey in Lake Michigan. And this is due to the abundance of Chinook salmon throughout much of this time period. It's also due to the simple fact that Chinook salmon are effective, fast-growing predators. It's common to see Chinook salmon in Lake Michigan that are 20 plus pounds. The state record Chinook salmon in Wisconsin caught in the 1990s was almost 45 pounds. Regardless, Chinook salmon are a relatively short-lived fish. Recently at our spawning weirs in Wisconsin, most of the Chinook that we're seeing are 2 and 3 years old. We see a few 4-year-olds. It's very rare to see a 5-year-old. So they're short-lived fish, but they can grow quick if they can get on the forage. For these reasons, recent stocking reductions to balance predator-prey in the lake have focused on Chinook salmon. So I previously showed biomass and abundance of Chinook salmon has come down. Likewise, consumption by Chinook salmon has also come down. So this slide just shows a snapshot of consumption for 2017. On the top, we look at annual consumption estimates for each of the different predators. On the bottom, I look at Chinook salmon consumption versus all the other predators combined. So despite the reduced consumption by Chinook, if we look at individual species, Chinook salmon still remain the dominant consumer of prey in the lake. However, in recent years, we now see that all the other predators collectively are actually having a bigger impact on prey consumption than Chinook salmon are having. So because of this kind of dominance of Chinook salmon throughout much of this time period, a lot of the management effort has focused on Chinook salmon. So the statistical catch-at-age model for Chinook salmon was recently developed by Eyab Sahaya. We also update the catch-at-age model for Chinook salmon every single year. For the other predator models, we're sort of using the best available methods that we have, but the underlying methods of some of those models could use improvement. Additionally, we do not update those other predator models every year, which is why you can see since 2008, the consumption by those other predators has remained constant. Now, with that said, especially considering some of these recent ecosystem changes that we've seen, now might be an important time to start taking a closer look at some of those other predators. and indeed some of that work is ongoing. This is total lake-wide biomass for all the different predators based on some preliminary efforts to update these other catch-at-age models. And what these show is that particularly lake trout and steelhead may be having a bigger impact on the forage base than previous estimates. I also want to acknowledge that Rick Clark at the QFC recently received funding to develop and expand the catch-at-age model for lake trout. So that's pretty exciting and should provide a lot of good new information about lake trout, but it's also a pretty big effort. It'll probably be about 2 years out yet before we're able to start using that model. And then I also want to acknowledge that there's been a lot of discussion about the diet proportions used in the consumption models. Certainly as the diets and ecosystem change in Lake Michigan, taking a look at what diet proportions are used in the modeling might be important. So a lot of these thoughts, this ongoing work is certainly good and important, but for the purpose of today's presentation, we're going to use just kind of the status quo approach, which is based on these consumption estimates shown here. So additional pieces of information that feed into the catch-at-age model for alewife is the USGS forage surveys. So Dave Warner just gave a presentation on these surveys, but I'll just provide a very quick overview. Generally, these lake-wide surveys have documented low abundance and biomass of forage throughout Lake Michigan. They've also shown a truncated size and age structure. So we used to see older, bigger alewife. Now we typically see smaller, younger alewife. And then these surveys have also shown somewhat of a patchy distribution of alewife throughout Lake Michigan. And kind of two primary mechanisms that have been thought to be contributing towards these patterns. One of the main ones is pretty significant top-down predation pressure by both stocked and wild salmonids, and then also possibly bottom-up impacts from invasive mussels. And the end result is low alewife biomass. So this figure shows the recently updated catch-at-age model estimate for total lake-wide biomass of alewife. The long-term average here has been 242 kilotons, and we've been below that average now for the past 14 years, since 2004, and we've actually been below 100 kilotons now for the past 3 years. So if we look at these two different data sets collectively, we can divide total lake-wide Chinook salmon biomass divided by total lake-wide alewife biomass, and we can look at this data in terms of a ratio. So generally with high Chinook salmon biomass and low alewife biomass, we've seen an increasing predator-prey ratio. So this is the lake-wide biomass of Chinook salmon divided by alewife divided by year. And I took a little bit of a step back here. This is actually the results of the PPR with data updated just through 2015. And in order to help interpret what this ratio means, we've established some specific reference points. So a target reference point of 0.05 essentially shows a balanced predator-prey population. It's a management goal or a target, whereas an upper limit of 0.10 represents an unbalanced system with too many predators and not enough forage. We've used several different criteria to establish these different reference points. The one that I'd like to highlight is a comparison with Lake Huron. So we've seen in several talks this week that Lakes Michigan and Huron are similar in many ways. This is the Mackinac Bridge connecting the upper and lower peninsulas of Michigan. On one side of the bridge you have Lake Michigan, the other side of the bridge you have Lake Huron. The two lakes sit at the same elevation, they're directly connected, there's free movement of fish and water from one lake to the other. This is just a side-by-side comparison of the USGS forage surveys for Lakes Michigan and Huron. This is updated just through the 2000s, but I wanted to show it just to drive home the point that we saw very similar patterns between the two lakes. So in Lake Huron, the alewife population collapsed in 2003. This was following a 5-year period during which the estimated Chinook to alewife ratio averaged 0.11. And subsequently, the Chinook salmon population collapsed in 2006. So we learned from Lake Huron, and going back to Lake Michigan now, that 0.10 is a good place not to be. And based on the 2015 model results, you can see that we were right at or above that upper limit on 2 occasions. Now on this next slide, I will overlay the predator-prey ratio results that we calculated last year. So this purple line is going to show the 2016 model. And what we saw when we ran the predator-prey ratio last year was that the 2016 ratio was 0.07. And then one thing that particularly stood out is the previous time series for the ratio actually came down. And most notably, the 2015 estimate based on the 2015 model was above target. The 2015 ratio based on the 2016 model came down to, above the upper limit, dropped down to just above target. So I think initially some of the managers were kind of surprised to see this shift, and what it highlighted was that really the tail end of a statistical catch-age model tends to be the most uncertain. So a very simplified explanation is that every time you add another year of data to a catch-age model, you're providing information that produces the current estimate, but you're also providing information that recalculates the entire time series. So a 2-year-old fish last year is a 3-year-old fish this year. As you gain more information on that year class, you're gaining new information that can produce a new and a better estimate for the time series. So that's kind of a general example or explanation. If we split the ratio back apart into its 2 separate components, we can look a little bit more specifically at what was driving that difference. So this shows total lake-wide biomass of Chinook salmon based on the 2015 model. And I will overlay now the estimate based on the 2016 model. And we saw very similar patterns between the 2 estimates. This is the total lake-wide biomass of alewife based on the 2015 model. And again, I'll overlay the 2016 model. Overall, we saw very similar trends. Regardless of which model you look at, we saw record low alewife biomass. But if you zoom in to recent years, we can look at more of the fine scale differences in these 2 estimates. And you can see that for year 2015, based on the 2015 model, we had an estimate of 37 kilotons. For 2015, based on the 2016 model, we had 75 kilotons. So they're both very low estimates, but one is just over double the amount of alewife. So just to highlight that simple math, this shows the PPR for 2015 based on the 2015 model runs. This shows the PPR for 2015 based on the 2016 model runs. So in both cases, Chinook salmon biomass was the same at just under 4 kilotons. However, alewife biomass just over doubled, and that was enough to bring the predator-prey ratio down. So now, again, this here is the predator-prey ratio based on the 2015 and the 2016 model estimates, and I'm going to overlay with a yellow line the recently completed 2017 predator-prey ratio. And overall, we saw similar patterns to the previous years, but a slight decrease in the ratio. And again, if we break the ratio apart into the components, we can look at the difference between the 2 model runs. So this here is the 2015 and 16 model runs for Chinook salmon biomass, and the same for alewife biomass. And if we overlay the 2017 model, we saw very similar patterns for Chinook biomass. If we overlay the alewife model, we saw very similar patterns for alewife biomass. But again, if we zoom in to the recent years, we can look at the more fine scale differences, and the Chinook models were very similar. The alewife model for 2016, the 2016 model produced an estimate of 67 kilotons. The 2017 model produced an estimate of 87 kilotons. So it was a slight change of about 19 kilotons. which was enough to bring the ratio down a little bit. It wasn't quite the difference that we saw last year, but we did see a slight decrease in that estimate. So overall, this is our most recently completed predator-prey ratio. For 2017, the PPR was 0.058, and we've now been just above target for the past 3 years. Overall, I think that it's somewhat positive and encouraging to see that the predator-prey ratio has come down. I think the recent stocking reductions and reduction of Chinook salmon biomass and consumption has been a major component to that. However, alewife biomass is still at a record low. The PPR is still above target, and if you look just at the last 3 years, we do still see a somewhat upward trajectory. So in addition to the predator-prey ratio analysis, every year we also update a series of what we call auxiliary indicators. And these indicators are designed just to look at simple data sets plotted through time so we can evaluate trends. They're designed to kind of complement and ground truth what we're seeing in the predator-prey ratio. And the first two indicators here are average weight of age 3 female Chinook salmon and standard weight of a 35-inch Chinook salmon. Simply put, how big are the fish? You know, the size and growth of a fish can be a very good indicator of predator-prey balance. A big fish is going to suggest they're eating well. A small fish is going to suggest they're not eating enough. The next one looks at targeted harvest of Chinook salmon by charter anglers. There's a lot of charter fishermen throughout Lake Michigan. They're good at catching fish. They spend a lot of time out on the water. So certainly it's important to take a look at what their catch rates are. And their catch rates can provide somewhat of an indication of Chinook salmon abundance. And then the last one looks at lake-wide sport harvested weight as a percent composition by species. So although the predator-prey ratio focuses on Chinook salmon and alewife, certainly there are many other salmonids in the lake that are targeted, and this provides just kind of a simple snapshot of what's going on with some of those other species in the fishery. We also have an indicator that looks at alewife age structure based on the catch-at-age model estimates. I didn't have a chance to fit that one into the talk today, but I will be including that in the written report. So first we'll look at the average weight of age 3 female Chinook salmon from fall spawning surveys. This approach looks at data sets collected from throughout the lake, including spawning weirs in Wisconsin, spawning weirs in Michigan, and also fall electrofishing harbor surveys in the state of Illinois. And in 2017, we had 931 age 3 females that were included in this sample. And you can see the distribution of samples from throughout the lake. Wisconsin generally has pretty big sample sizes here, and that's simply due to the fact that in collaboration with the U.S. Fish and Wildlife Service, we collect a lot of coated wire tag snouts at our weirs, so we have a lot of known age 3 fish that we can contribute to the sample. And this shows the average weight of these age 3 female Chinook salmon for 2017 per location. Generally, we saw similar trends throughout the lake. This average weight ranged from 15 pounds up to 18 pounds. Generally, fish in Wisconsin tended to run a little bit bigger. So this is the same data, but plotted on a time series. So the average weight for each of these different locations through time, updated through 2017. Overall, we saw similar patterns throughout the lake. Again, you can see these Wisconsin fish. So the blue line here is Strawberry Creek. Tend to be a little bit bigger. I was thinking about this a little bit last night, and I don't really have a good explanation for why the Wisconsin fish are bigger. The mass marking program results suggest that during the summer, the fish are out, pretty much mixed throughout the lake, chasing the alewife. So you would kind of expect to see similar growth. One possible explanation could be that as these fish mature and they start to move back to their spawning rivers, maybe there's some local differences in forage, so you're seeing different growth late in life. Once these fish enter the rivers, they typically aren't actively feeding, so duration of time spent in the rivers might be coming into play here too. Chinook or Strawberry Creek is a relatively short run. It's less than a half mile from the lake up to the weir, so the fish tend to be in pretty good condition when they enter the weir. Some of the other weirs throughout the lake might have longer run times, so maybe if the fish are in the rivers longer, they might be losing some of their growth and their size late in life. Those are just some possible ideas. If we compare these differences in size from 2016 to 2017, throughout the lake we saw an increase in size, with the Michigan fish generally increasing most in size, followed by the Wisconsin fish. The one exception was Strawberry Creek. The average weight at Strawberry Creek last year was 19 pounds. The average weight this year was 18.4 pounds. So we actually saw a slight decrease in size between these 2 years at Strawberry Creek. So if we combine all of these different data sets using a weighted average, this looks at the total lake-wide average weight of an age 3 female Chinook salmon updated through 2017. And our value for 2017 was 17.8 pounds. The long-term average was 15.5 pounds. We saw generally some big fish in the 90s, and then we also saw big fish in 2013, 16, and 17 at about 18 to 19 pounds. However, the overall trend during recent years is that we've seen a lot of small fish, likely due to low alewife biomass. 13 of the past 16 years have been below average. So another interesting thing that we've seen is a high degree of variability in weights during recent years. So just as an example, in 2012, the average weight here was 11.8 pounds, and the next year in 2013, it jumped all the way up to 18.9 pounds. So it was a 7.1 pound difference. The red numbers along this figure represent, as an absolute value, the change in weight from one year to the next. And on the next slide, I'll simplify this a little bit. And this shows that change in weight from one year to the next as a bar graph. And what we see is from 1986 to 2012, on average, that change in weight from one year to the next was 1 pound. But in the recent years, it's been on average almost 4 pounds, some years as much as a 7 pound swing. And this is somewhat concerning and seems to suggest almost somewhat of an instability within the ecosystem. What we think might be driving this pattern is availability of young alewife. So although alewife biomass in Lake Michigan right now is low, as Dave talked about, every once in a while we do get a good year class. And we think that availability or not of these young alewife may be driving whether or not we see a big upswing or downswing in some of these growth patterns. So, and just for a comparison, this is the average weight again, and in the thicker red line here, I just provided a comparison with the Swan River weir in Lake Huron, and overall similar patterns between the two lakes. So the next calculation looks at the standard weight of a 35-inch Chinook salmon, and this takes into consideration creel and mass marking samples collected from July 1st to August 15th. So these are midsummer fish that are collected before these fish start returning back to their spawning rivers. And this just provides a simplified explanation of the standard weight calculation. So we have weight versus length. Each dot represents an individual fish. And where these lines match up, you can get the standard weight. So in this particular case, the standard weight of a 35-inch Chinook salmon is 17.7 pounds. So this just shows the sample sizes for these standard weight collections through time. You see a big spike in the sample size in 2012. Prior, it was hundreds of fish. Recently, we've seen thousands of fish. And this is due to contributions from the Great Lakes Mass Marking Program. We did see a slight step down in 2017. That's possibly due to lower harvest and availability of samples, but probably a big part of it was a little bit of a change in the effort. Some of the mass marking crews started a little bit later than normal. But regardless, we've got a ton of samples, and this is just one example of the many pieces of data that are provided by the Mass Marking Program for this analysis. So I just want to thank and acknowledge the Mass Marking Program for all that information. And then for 2017, our sample size was 2,700 fish, and this just shows the sample sizes across the lake for creel program in yellow and the mass marking program in blue. Over 80% of the samples this last year came from the mass marking program. So this shows for 2017 the length weight scatter plots for each of the individual sampling methods and locations. We do a regression analysis on each of these and conduct a weighted average to look at the overall lake-wide standard weight of a 35-inch Chinook salmon. And for 2017, that number was 18.2 pounds. The long-term average is 17.1 pounds. And again, we see big fish in the 90s. We saw big fish in some recent years. These patterns are similar to what we saw in the weight at age 3. Overall, during recent years, we've seen a lot of relatively small fish. 10 of the past 14 years have been below average, and we actually hit an all-time low in 2012. So similar to the weight at age 3, we're seeing a lot of variability, not quite as evident, but greater variability in year-to-year standard weights than what we saw historically. And this just looks at the standard weight for each of the states separately. Again, we're seeing similar patterns across the lake. And then this is just a comparison of a standard weight with Lake Huron. So again, the alewife population collapsed in Lake Huron in 2003. Overall, we're seeing similar patterns with Michigan, but we haven't seen fish quite as small in Lake Michigan as we experienced in Lake Huron. So next is target harvest per hour of Chinook salmon by charter boats. And first I'll take a look at harvest. So on average, the harvest by charter boats throughout the lake has been about 103,000 Chinook salmon annually. We've seen some high years, including 2012, where we've had over 200,000 Chinook salmon harvested. However, in recent years, this harvest has come down. 2012, just over 50,000 Chinook salmon were harvested, which was the lowest number we've seen since 1995. And the past 5 years have been below this long-term average. And again, if we look at harvest by charter boats for each of the states, we see similar patterns throughout the lake. And then next we can look at effort by charter boats. So this is in terms of hours fished. And overall, effort has remained somewhat constant. It's fluctuated a little bit around this average. For 2017, these hours were 646,000 hours fished, and we were pretty much just at that long-term average. And we see if we look at the statewide effort, or effort for each state, in 2004 we saw a bit of a shift between Wisconsin and Michigan. So Wisconsin now generally puts in the most effort, followed by Michigan, Illinois, and Indiana. And if we look at this as a harvest per effort, with declining harvest and relatively constant effort, the catch per effort has come down. And this just shows the catch per effort for each of the specific states. So even though harvest has recently been higher in Wisconsin, we also put in more effort in Wisconsin. So if you look at it in terms of a catch per effort, Wisconsin and Michigan are actually very comparable. And then the last auxiliary indicator that I'll share is the lake-wide sport harvested weight, expressed as a percent composition by species. And this information, again, percent composition by species, this is lake-wide harvest from the extraction report that's completed every year. And throughout much of this time series, Chinook salmon have by far been the dominant component. This percent composition peaked at 85% in 2006 and since has come down. Another way to look at this same data, instead of looking at it as a percent, is to simply look at lake-wide sport harvest in pounds for each of the individual species. I'll acknowledge that the y-axis on these figures are not the same, so you can't do a direct comparison, but I'm showing it just to show some of the basic trends. So Chinook salmon harvest has generally been decreasing. Lake trout harvest has generally been increasing from 195,000 pounds in 2006 to 812,000 pounds in 2016. Rainbow trout and coho harvest has remained relatively constant. and we've seen a decrease in the overall harvest and brown trout harvest. So just to summarize, based on recent 2017 modeling, PPR values for the past 3 years were each just above the established target of 0.05. These recent PPR values are down compared to a high of 0.09 in 2013. Alewife biomass remains low and has been under 100 kilotons now for the past 3 years. And Chinook salmon biomass peaked at 14.4 kilotons in 2013, but since has declined following several stocking reductions and was 14.7 kilotons in 2017. So Chinook salmon weights have generally been below average for the past 15 years, although some recent years have produced big fish with high year-to-year variability in these weights. Total harvest for Chinook salmon and harvest per hour by charter boats has been decreasing since 2007. While sport harvested weight for Chinook salmon has decreased, harvest of lake trout has slightly increased. So because a lot of these results just recently became available, I haven't had a chance yet to complete the written report for this meeting, but I just want to acknowledge that last year's report is available online, and we hope to get this year's report completed and posted online very shortly here. So the predator-prey ratio, as I mentioned earlier, was just recently developed in 2012 to 2014, so it's a relatively new approach. Overall, I think it's a very good, very comprehensive way to provide a way to evaluate balance between Chinook salmon and alewife. But already we are starting to brainstorm several different ideas and thoughts on possibly improving and expanding the predator-prey ratio. And this is just a list of some possible ideas that were generated at a recent Salmonid working group and Lake Michigan Technical Committee meeting. And some of these things include trying to expand some of the other predator catch-at-age models, trying to establish some type of variability or confidence level in some of these predator-prey ratio estimates, and then also trying to look at some of the diet proportions and how we might be able to improve or change those in the modeling. So I presented this slide at the last March meeting, but I think it drives home a pretty important point. So I'm going to conclude just by mentioning that indeed the predator-prey ratio is a ratio. And because it's a ratio, there are very different scenarios that can produce the same result of 0.05. So in 2013, the total lake-wide biomass of Chinook salmon was estimated to be 14.7 million kilograms. At that time, hypothetically, if we would have had 294 million kilograms of alewife, we would have had a balance ratio of 0.05. In 2015, the total lake-wide biomass of Chinook salmon was estimated to be 3.9 million kilograms. Hypothetically, if we had 17 or 79 million kilograms of alewife, we would have had a balance ratio of 0.05. So two very different scenarios that both produced the same balance of 0.05. So just because we're at a balanced ratio of 0.05, just because we're seeing big fish out in the lake, does not necessarily mean that the lake can sustain or support increased levels of stocking. So trying to achieve this appropriate balance between number stocked, species stocked, angler expectations can be extremely complex and challenging, but I hope that the information presented today will be helpful in making some of those future decisions. So again, I just want to thank everybody that contributed to this talk, and again, a special thanks to the modeling team that pulled together a lot of these results just last week. And with that, I can take any questions.